Welcome to lecture 23, matrix inverses, inverting a matrix and how to calculate it. All right, so we've been learning a little bit about matrices, and we're going to talk about matrix multiplication and the matrix inverse. I'm assuming all of you have seen what matrix multiplication is, and we're going to focus now on looking at the matrix inverse. We're going to be working on square n by n matrices. And the definition of the matrix inverse is simply A times A inverse equals the identity, or A inverse times A is equal to the identity. The inverse always satisfies both of those. And I is the identity matrix, which is a diagonal matrix with all ones along the diagonal. Now we define a specific symbol called delta ij to equal 1 if I equals j and 0 otherwise. This is called the Kramers delta function. You've probably seen it before. You're definitely going to see it a lot more in your upper division physics classes. So using that Kramers delta function, we can rewrite the definition of the inverse as the sum over j, A inverse ij, ajk equals delta ik. And similarly, the sum over j, aij, ajk inverse equals delta ik, where the sum over j is over the n elements from 1 to little n. And so this is the definition of what the inverse is. It's simply using the matrix multiplication definition and equating that to the identity matrix. So the first thing we want to establish is that the inverse is unique. So suppose B is also an inverse of A, which means A times B is equal to I. And then if I multiply on both sides by A inverse, I get A inverse times A times B will equal A inverse times I. Well, I can use the associative property to regroup and write that as A inverse dot A times B. And that's equal to A inverse, because A inverse times the identity is simply equal to A inverse. Any matrix times the identity is equal to the matrix itself. Now, A inverse times A, by the definition of the inverse, is equal to 1, or the identity. So I have I times B is equal to A inverse, and now using the property of the identity again, I find that becomes B equals A inverse. So if I thought I had another inverse of A, that we'll call B, we find that just from the properties of the inverse, B must equal A inverse. So we can't have an inverse of A that is any different from the one unique inverse, which we call A inverse. All right, let's now recall what a cofactor is. It was minus 1 to the I plus j of the determinant of what I'll call A sub ij, where A sub ij is the matrix A with the ith row and the jth column removed. And in particular, we showed that you could expand the determinant in terms of these cofactors. One of the formulas we found was that the determinant of A was the sum j equals 1 to n of aij cij, with cij being this cofactor. And now we're going to define something new. We're going to define qij to be the sum over k of aik cjk. Now notice, if I is equal to j, then this is just the determinant. So the determinant of A is equal to qii, and the interesting thing is if I is not equal to j, then we can interpret this as the determinant of a matrix that is constructed from A by replacing the ith row with the jth row. See, if I had A jk cjk, that would be the determinant for the matrix A. But I've replaced that jth row, ajk, with aik. So I've replaced the jth row by the ith row. But we know the determinant of any matrix that has two rows that are the same is just equal to 0. So qij equals 0 if I doesn't equal j. And that means I can write qij is equal to determinant of A times delta ij. That identity is going to become very important in just a moment. So it turns out we can actually get an analytic formula for the inverse. And I'm going to just remind you of this formula that we just derived about qij. We're going to let absolute value of A be the determinant of A. So we're going to call that the determinant of A. so that Qij is equal to determinant of A times delta Ij. And the claim is that A inverse Ij, whose elements are A inverse Ij, is equal to Cji divided by the determinant of A. Note that it's Cji, not Cij. It's very important you note that the I and the j have been interchanged in this definition of the inverse. So how do we check that it's an inverse? We use the property of the inverse and see whether or not it holds. So let's look at the ij element of A times A inverse, assuming this result holds for A inverse. So I substitute in for AKJ inverse with CJK divided by the determinant of A. Remember, because we're flipping the K with the J when we write it in terms of those cofactors. And now look at that formula. The sum over K is just Qij. Well, I know Qij is equal to the determinant of A times delta Ij. And now the determinant of A is going to cancel in the numerator and the denominator. I'm just left with delta Ij. But that then says A times A inverse is equal to the identity. So indeed, we found the inverse matrix. And so we have this explicit formula for the inverse. Now, since we already showed that the inverse is unique, this is the unique formula for the inverse. Unfortunately, this formula isn't very practical, because in order to calculate it, I have to calculate n squared n minus 1 by n minus 1 matrix determinants, and that's difficult if n is large. It takes a lot of computation to do that. Now, there's another property that we can immediately learn from the properties of determinants. Since the determinant of the identity matrix is equal to 1, and that's simply because it's a diagonal matrix, which means its determinant is the product of all its diagonal elements, and all the diagonal elements are 1, so the determinant of the identity is 1. Then we find the determinant of A times B is then because we know already that the determinant of A times B is determinant of A times determinant of B, if I look at the defining equation for the inverse, I find the determinant of A times the determinant of A inverse is equal to the determinant of the identity, which is just 1. And so we learn the determinant of A inverse is 1 over the determinant of A. And this tells us that we can find the inverse of a matrix if the determinant of the matrix is non-zero. If the determinant is 0, then the determinant of A inverse would be infinity, and it effectively is telling us that there is no A inverse that we can find. But otherwise, the determinant is a finite number, and so we indeed can find the inverse matrix A inverse. All right, let's go through an example of how this works, how we could apply this formula for a matrix. So we're going to look at the inverse of a 3 by 3 matrix. It's 1, 2, 1, minus 1, 0, 1, 1, 2, 3. That's our 3 by 3 matrix. And let's calculate its determinant. I'm going to calculate it in the way that you know. I'm going to first look at the 3 diagonals that point in the minus 1 slope, and I'm going to look at the 3 diagonals that point with the plus 1 slope. So I'm going to get 1 times 0 times 3, that's 0. I'm going to get minus 1 times 2 times, I'm going to get 2 times 1 times 1, that's 2. And I'm going to get minus 1 times 2 times 1, that's minus 2. And then I'm going to get minus 1 times 0 times 1, that's 0. I'm going to get minus 1 times 1 times 2, that's minus 2. And I'm going to get minus 1 times 2 times 3, that becomes plus 6. And so when I add them all together, I get 4. So that's the determinant of this matrix. It's equal to 4. Now I have to calculate the matrix of cofactors. Well, this takes quite a bit of work to do. So I'm going to show you explicitly how a couple of these elements work, and then you just have to go through for yourself and verify that you can do the other ones. So let's look at the 1, 1 element. So minus 1 to the 1 plus 1 is equal to minus 1 squared, which is equal to 1. So there's a plus sign in front of that element. And I have to cross off the first row and the first column, so I'm left with the matrix 0, 1, 2, 3. So I have to take the determinant of 0, 1, 2, 3, which is 0 minus 2, so it's equal to minus 2. And that is the 1, 1 element of the matrix of cofactors. The 1, 2 element, I have to cross off the top row and the second column. I'm left with minus 1, 1, 1, 3. And because minus 1 to the I plus j is odd, there's a minus 1 out in front, When I calculate that determinant, I get minus 3 minus 1, which is minus 4, but then I multiply it by minus 1, and I get plus 4, and so forth. So you should verify for yourself, going very carefully through it, that you can evaluate all of the terms in these cofactors, and you get this matrix on the right-hand side, minus 2, 4, minus 2, minus 4, 2, 0, and 2 minus 2, 2. All right, now we have to plug into our formula. Remember, the inverse was equal to the transpose of that matrix of cofactors divided by the determinant of A. So I first have to transpose that matrix and then divide it by 4. So I get minus 1/2, I get minus 1 because of the transpose, and I get 1/2 in the upper row. I get 1 because of the transpose, 1/2, 0, I'm sorry, minus 1/2, and I get minus 1/2, 0, 1/2 for the bottom row. Now, if you multiply this times the matrix, I'll just work out the first row times the first column. 1, 2, 1 times minus 1/2, 1 minus 1/2 will be 1 times minus 1/2, that's minus 1/2, plus 2 times 1, that is 2, plus 1 times minus 1/2, that's minus 1/2, so I have 2 minus 1/2, which is equal to 2 minus 1, which is equal to 1. And so indeed that is the 1, 1 element of the identity matrix. And so you should carefully go through and verify all of the other matrix elements work when you multiply A times A inverse, that you indeed get the identity matrix. All right, let's look at some other ways that we can calculate the inverse. One of the most common ways is by using row reduction. So row reduction ends up being a much more efficient way to calculate the inverse than using the explicit formula. There are a couple of differences from what we did before with row reduction. First, our augmented matrix now is going to include the full identity matrix instead of just one column vector B, because we have to do the row reduction on each one of those different columns to determine the full matrix. And then the second thing we're going to do is we're actually going to make zeros both above and below the diagonal, and we're also going to renormalize the diagonal so that the diagonal is 1 for the matrix on the left after we've done all the row reduction. And this will be clear after we go through an example. So let's start by writing our augmented matrix. We have the original matrix A on the left, we have the identity matrix on the right, and now I'm going to make zeros in the first column below in the second and the third row. So I'm going to add the first row to the second row. That's going to give me 0, 2, 2, 1, 1, 0. I'm going to subtract the first row from the third row. That's going to give me 0, 0, 2, minus 1, 0, 1. Okay. Now it turns out we're really lucky in this case. We actually got a 0 as well in the third row, giving us this lower triangular set of zeros. We're now going to renormalize the second row and the third row to get 1s on the diagonal. So we're going to divide by 2, and we're going to get then 1, 2, 1, 0, 1, 1, 0, 0, 1 on the left, and we'll get 1, 0, 0, 1/2, 1/2, 0, minus 1/2, 0, 1/2 on the right. Okay, now we want to do row reduction to create a triangle of zeros in the upper right part of the matrix that's on the left part of this augmented matrix. So I'm going to subtract row 3 from row 2. When I subtract row 3 from row 2, I'm going to get 0, 1, 0. I'm going to get 1/2 minus minus 1/2. That's going to give me 1. I'm going to get 1/2 minus 0. That's going to give me 1/2. And I'm going to get 0 minus 1/2. That's going to give me minus 1/2. Now I also have to subtract row 3 from row 1, and I'm going to get 1 minus 1 is 0. I'm going to get 1 minus minus 1/2. That's going to be 3/2. I'm going to get 0 minus 0, and I'm going to get 0 minus 1/2. That's going to be minus 1/2. And now I have only one more 0 I have to create. I have to make a 0 in that first row in that second element. So I'm going to multiply 2 times the second row and subtract it from the first. So I get 1, 0, 0. And then I'm going to have 3/2 minus 2. That makes it a minus 1/2. I'm going to have 0 minus 1. That gives me a minus 1. I'm going to have minus 1/2 minus 1 minus a minus 1. That's going to give me plus 1/2. And so now you can see the augmented matrix has become the matrix inverse. That's exactly the same matrix inverse as we had found in the previous slide. And so this is the way in which you do it via row reduction, and it is actually a much easier way of doing it than trying to do anything with that matrix of cofactors, which is prohibitively difficult to calculate. Okay, we're going to now look at something called Kramers Rule. Kramers Rule is using that formula in terms of those cofactors in order to solve our original linear equation, ax equals b. And we do it by multiplying by A inverse. So we find x is equal to A inverse b. And now we just plug in what A inverse is by writing it as 1 over the determinant, the sum over j, bj, cji, with cji being that matrix of cofactors. And the way that we can think of this is we take the matrix A and we replace the ith column by the vector b. We compute the determinant, and then we divide by the whole thing by the determinant of A to get the corresponding element of x. Now, this method is useful only in a couple of cases. If the matrix A is small, like a 2 by 2, maybe a 3 by 3, it might be okay to do this. If we want only one or a few components of x, if for some reason we only need, say, the 19th component of x, this might actually be an effective way of calculating the element for just that one particular element. Or it might be useful if the matrix A has many zeros, because if the matrix A has many zeros, then it might be easy to calculate these different determinants via these cofactors. Now I want to end with two definitions. The first one is an orthogonal matrix. That's constructed from n orthogonal unit vectors, either in columns or in rows. It turns out that an orthogonal matrix satisfies O inverse is equal to O transpose. So I can very quickly calculate the inverse of an orthogonal matrix if I know that it's orthogonal, because all I have to do is calculate the transpose. Another matrix that's very important in physics is called a unitary matrix. This is constructed from n orthonormal unit vectors that are coming from a complex vector space. So all of the elements of the vector space involve complex numbers. It satisfies U inverse is equal to U complex conjugate transpose. So the star here denotes complex conjugation. And in both of these cases, the inverse is easy to form. What we find for the unitary matrix is that the inverse is what's called the Hermitian conjugate. It's the transpose complex conjugate of the matrix U. And that ends our discussion of matrix inverses for this lecture.